Hey guys, and welcome back to Up Chem. In this video, we're going to be starting a new unit. So we're going to be looking at the unit 2 and 12 content, which is atomic structure. And this is going to twin well with unit 1 and give us a really good foundation. So in this lesson, we are going to be looking at the structure of subatomic particles, and then we're going to focus on mass spectroscopy and how we can use that to determine the relative isotopic mass. So first, let's look at the structure of the atom. So we're going to use the Bohr model of the atom, which was developed at the turn of the last century, in which we have a positive center with electrons around the outside. Now, in this model, we have the vast majority of atoms, and the vast majority of matter, therefore, as empty space. So atoms are indeed mainly empty space. Now, this developed after what previously was thought of as the plum pudding model, in which you had kind of a positive kind of structure that had these little negative charges in it. You can think of this, these were considered the negative plums in the positive pudding. Apparently, plum pudding has gone out of fashion since 1911. This model was found to be incorrect in Rutherford's experiment, where he fired particles at a gold foil sheet and found that most of the particles went through the atoms, and this was obviously due to the empty space. So, what are the actual components of this model, and what is the structure? Well, as we said, we have a positive charge center with electrons in orbitals around the outside. Protons in the center of the atom have a positive charge, and the electrons around the outside have a negative charge. There are also the presence of another subatomic particle in the center called neutrons. These have zero charge, they do not contribute to the overall charge, and together the protons and neutrons are called the nucleus, which has an overall positive charge. Now, these subatomic particles have different masses and different charges, as we've mentioned. So the mass of the proton and the neutron are effectively, to all intents and purposes, the same, whereas the charge, obviously different charge here measured in coulombs, whereas with the electron is quite significantly smaller by orders of magnitude than the proton and neutron, but its charge obviously exactly the same in magnitude of that of the proton. So in relative terms, we can see that the electron is roughly about 1/1800 times the size of the proton and the neutron. So the periodic table is effectively a tool that tells us these things about all of the atoms. So on your periodic table in your data booklet, you get things that look like this. This is for sodium. So we have a couple of numbers and symbols we can look at. So this top number is what's called the atomic or proton number. This tells us the number of protons that are in the nucleus. This is the thing that defines what an element is. The same number of protons, you've got the same element. That is the key to knowing what element you have. In a species with no charge, then we know that that number is going to be equal to the number of electrons, because there's no charge. So to balance the charge, there has to be an equal number of electrons and protons. Now, obviously, that's different if there's a charged species. So where does this number come from? Well, this number is the mass number, which is equal to the protons plus the neutrons. Now, obviously, you've noticed here, well, how do we get a decimal number of neutrons? This is taking into account the fact that we have different isotopes. So this is the relative isotopic mass. And this takes into account all of the different isotopes that naturally occur and gives us an average of their abundance. So we can have this, just to define isotope, we have the same number of protons, but a different number of neutrons. So an example for sodium here would be to have the Na22 and the La23 isotope. You'll see the proton number the same, but the mass number is different. So the relative isotopic mass tells us something about their relative abundance, which is something we're going to consider more in this video. But first, we can use this information to determine more about a species. So let's take something like this. We have a mass number, we have protons, and we have a charge. So how do we go about finding neutrons, for example? Well, we know 19 minus 9, which is mass number minus our protons, is 10. Now we have a charge of minus 1. Protons would be equal to electrons, but we've got an extra electron, which is going to give us 10 electrons because of our minus 1 charge. Now we know the atomic number is always going to be equal to our number of protons, so that is going to be 9. So then we can look at the periodic table and we see that is going to be fluorine, but with a negative charge. Let's have a look at something else. So let's take this species here. So we've got nitrogen 3 minus 14. So we've got our mass number and we've got our symbol here. We know that our atomic number is 7 because we have nitrogen, and that gives us our proton number. So we've got 7 protons. We've got 14 overall mass, so we must have 7 neutrons. We would have the same number of protons and electrons, but we've got a negative 3 charge, which gives us 10 electrons. So you can see how we can use this to find so much out about an atom just by knowing 1 or 2 parts of this. So I want you to have a go at this table, copy and completing it, just to give yourself some real practice. So just pause the video and take your time with that. Okay, so here are the answers to that table. You can pause the video so you can double check your answers. So we're just getting used to using the periodic table to find out this kind of information. So a common question is, where does all this information come from? And one part of that is through mass spectrometry. So we're going to look first about how this works and then about the application. So it happens in 4 stages. We've got ionization, we've got acceleration, we've got deflection, and then we've got detection. And you do need to know those stages. So let's kind of follow a sample through a kind of schematic of this. So we have our sample, and the first thing we're going to do is we need to ionize this. So usually this is done by pushing the sample through kind of an electron cannon, if you like, something that bombards the sample with electrons. So the sample travels through from left to right, and then electrons are fired through the sample. And be careful to not be confused here, because we're going to make M plus ions. If the sample is M, we make M plus ions because the sample has loads of electrons around it. Now, we're not trying to add electrons with our electron cannon. We're actually using these high energy electrons to kind of knock electrons off of our sample and form an M plus ion. So we're actually going to be using positive ions, and then what that's going to do is that's going to go into a magnetic field which is going to accelerate these ions. Okay, now so only something that is ionized can be accelerated. We can't accelerate something that has not yet been ionized, so any sample that is not ionized will not be accelerated. This then gets to the deflector, which is another electromagnetic field. This time it will have its field lines going across the path of the acceleration. And because of that, and it's positively charged, that means there'll be an interaction between that field and the accelerated ion, which will cause a deviation of that path, which is the deflection, which will move it through to a detector. And that detector is a plate that when the positive ion hits it, it completes a circuit and then is detected. So this is significant because if we always deflect with the same amount of energy, then we know that any change in the deflection itself is going to be due to the mass of the sample, or indeed the mass of the different components of the sample. This is significant because it's allowed us to identify different isotopes. The reason is the path taken depends on the mass of the sample. So more specifically, the mass to charge ratio. So that's the MZ ratio, as we call that. So particles with a larger mass divided by charge ratio are deflected the least, and particles with a smaller mass to charge ratio are deflected the most. So you can think about this like a lorry and a car. In this situation, let's say both of these have the same brakes. Now, if they're going at the same speed and they have the same stopping power and they brake, which will stop first? Well, you already know that the lorry will take much longer to stop, and we can consider this a little bit like the deflection. In the deflection, we can think that something that is larger, because everything has +1 charge, or if everything has the same charge, then the smaller particles will deflect a lot more than the larger particles. Now, the amount with which something is deflected is going to tell us something about the mass of the particle itself. More specifically, it depends on the radius of the path that is taken. So that path will change as the mass changes. So you'll see, we can kind of imagine the circle that the path makes with the radius. So most of the ions that we make are +1 charge. So if they're all +1, then the amount of separation, the amount of change in this radius is due to mass alone. Now, if we do get some 2+ charge, then we're obviously going to alter that mz. So, and they will be deflected more because effectively we're going to double the size of charge and therefore half the mass charge ratio. So we can think about that like as putting better brakes on the lorry and car in the previous example. And this is why in general we try to aim for just a 1+ charge to make the spectra that we get from using this technique easier to interpret. So when we do get the spectra, they tend to look like this. We have positions of the peaks, which we have our mz value on the x-axis and abundance in percentage on the y-axis. The positions of the peaks along the x-axis give us the atomic mass, and the intensity of those relates to the relative abundance, and that can be scaled to 100%, and we adjust all the other values accordingly from the highest value. So we can use this to calculate the relative isotopic mass. And we can do that if we're given the spectra. Might not always be given the spectra, but if we are, we can use the spectra. So we're going to take the relative atomic mass of isotope A, whatever that may be, multiplied by the abundance. Then we're going to add to that the AR of isotope B times the abundance, all the way to as many as we have isotopes multiplied by the abundance, and that is going to equals our relative isotopic mass. It is also important to bear in mind when we're using this equation that when we say multiplied by abundance, we're talking here about the percentage abundance but given as a decimal. So we're going to have to convert all these percentages into a decimal value first. So that would look like this. All we have to do is divide by 100. So what does this look like? Well, we get 20 multiplied by our percentage that's already been converted here. We've got 0.26 for our 21, so we're going to do 0.0026. For our last one, we've got 8.82%, so that's going to become 0.0882. Add all those together and we get 20.18, which means that the relative isotopic mass is 20.18, which is what is on the periodic table. We can also get questions similar to this without the spectra and instead given as abundance values as we're given them here. So we're still going to use the same calculation that we used in the previous question, and then we're just going to plug in the values of mass and abundance. Remember, converting our percentage abundance into a decimal abundance. So we get 14 times 0.9963 multiplied by 15 times 0.0037, which is 14.0037. Slightly more accurate than on the IB periodic table, but that doesn't matter. So here we've got another question, exactly the same really, except we're looking at carbon. So we're going to use the same equation as we did before, and we're just going to plug in the values that this question gives us, which is 12 times, remember, converting our percentage abundance to a decimal, 0.9890 plus 13 multiplied by 0.0110 gives us 12.011. We could write that as the isotopic mass of carbon. Time for you to have a go at some questions though. So first question is nice and simple. Determine the relative atomic mass of chlorine given this data. Pause the video here. Pop 'em up! Hopefully you saw that we're just going to plug in the corresponding, remember, percentage converted to decimal value for each of the mass numbers, which is 35 and 37. Add those two together, which is going to give us 35.4846. Next question then has 3 different isotopes of silicon, but you're still going to use the same technique. Pause the video here. Pop 'em up! So you're still using the same technique, but now we've got 3, but just like we said, we could have 50 of these. It doesn't matter. We're just going to take the decimal conversion of the percentage abundance and multiply each. So it's 28, 29, and 30 in this case. And remember to divide each the percentage abundance by 100. When we add those all together, we get 28.1079. So another type of question you might come up against is calculating the isotopic abundance from the atomic weight. So here we've got nitrogen. So we've got nitrogen 14 and nitrogen 15. And it gives us the atomic weight. So that's the relative isotopic mass. And we want to find out the amount of each of these isotopes. So we've got unknowns here. So what we're going to do is we're going to designate nitrogen 14 as X. Now you could do this the other way around and use nitrogen 15. There's no significance to that. I'm just using nitrogen 14 here. So we've got the average and we're going to try and find the abundance of these 2 isotopes. We don't need the third isotope because there's only 2. As I've said, 14X, we're choosing X to be the abundance of the isotope nitrogen 14, is going to leave us with an assumption to make for our abundance of nitrogen 15. If X is the abundance of one isotope, then we can say the abundance of the other isotope must be 1 minus X, because remember our isotopes are decimals. You could think of that 100% minus the percent of X. Either way, I'm using the decimal straight away here. So that is obviously going to equals the overall atomic weight, which is given to us in the question as 14.007. So just to reiterate that, 14X, where X is the abundance of nitrogen 14, because we're designating X as the value for nitrogen 14's abundance, is going to leave us with plus 15 multiplied by 1 minus X, because there's only 2 isotopes. The total of both isotopes together must equals 1, so it would be 1 minus X. Now all we have to do is we have to solve this equation for X, so we have to expand the brackets out of the second part of the equation, and then we're going to solve to give us X, which in this case is 0.993. So now that we have a value for X, that gives us the percentage abundance for nitrogen 14, but it also means we can plug that value for X back into the equation to solve for the abundance of nitrogen 15. So 1 minus X is going to be equals to 0.007, which equals to 0.7%, giving us our abundance of both. You can think of this as an inverse process of what we did earlier on in the video. So we can see in this question about potassium, very similar to the last one, we've got 2 isotopes of potassium, and we've got the overall isotopic mass, which is 39.1. So once again, we're going to take the average AR, and then we're going to make X, I'm just going to make X equal to the potassium 39. Again, this process would work, you making X equals to potassium 41. It wouldn't make a difference either way. You can kind of think about this as we're assuming there are X number of potassium-39 in every 100 atoms of potassium, if that helps you. And because there's only 2 isotopes, once again, that means that 1 minus X must be the abundance for potassium-41. So then we just create the equation using the equation we've been using all lesson, but just plug in the assigned X values here. So we get 39X plus 41 times 1 minus X equals 39.1. We expand the brackets out to give us our X, and then we're just going to solve the equation for X, which is going to give us minus 2X equals minus 1.9. So X equals 0.95. So that means we get 95% abundance of our potassium-39. And we can also then put this value of X back into the 1 minus X expression to solve for potassium-41, which is going to give us 5% abundance for potassium-41. Okay, time for you to have a go, and just remember to use that X expression. First question about copper. Pause the video and have a go at that. Pop 'em up! Okay, so in this solution, I'm going to give the 63 copper isotope as X. So if you solved it the other way, your answer should still be exactly the same anyway if you gave X to be the 65 isotope. Or we plug these in and then have 65 as 1 minus X. Solve for X, which is going to give us X equals 0.72, which gives us 72% of the 63 isotope. Then we can already see it's 28, but we just put that value of X back into the 1 minus X expression and we get 0.28, which is 28%. So the only way these questions can get a little bit more advanced is if we're asked to find the abundances of isotopes when there are more than 2. So we're going to break this down into 3 main parts. The first part is we're going to construct an equation like we did before with X, but now we're going to have a component for Y. We can see in the question we've already been given silicon-29, so we're looking for silicon-28 and silicon-30. So I'm going to make silicon-28X, the abundance, and silicon-30Y. Again, wouldn't matter which way around you did this, you should still get the same answers at the end. We're then going to construct our equation, just like we did in the last 2 questions, but this time we're going to have a Y component because we can't express the abundance of silicon-30 just in terms of X. So we have 28X plus 29 multiplied by 0.0467 because we're already given silicon-29's abundance in the question. And then we're going to have plus 30Y, which is the abundance of silicon that we don't know yet, equals the isotopic abundance they gave us in the question. And we can also express this in the relative and simplified form, just giving the abundances, which is going to give us X plus 0.0467 plus Y is equal to 1. Just like it's out of 100 as it was in the previous question. But in these examples, what we're going to do is we're going to rearrange that second equation we formulated to give it equals to Y, and that's going to allow us to put that back into the original equation to have an expression that only includes one unknown. So when we do that, we get Y equals 1 minus 0.0467 minus X. So then what we're going to do is we're going to plug that, like I said, back into this top equation to have an expression only containing X. That's 28X plus 29 times 0.0467 plus 30 multiplied by our expression that we just rearranged because we're now subbing Y for this expression equals 28.0855. Now we can simplify and expand this expression out so that we get 28x plus 1.3543, which is that expression, plus 28.599 minus 30x is going to equals 28.0855, which gives us an X of 0.9339. So we now already know the percentage abundance of our silicon-28. We now know that that is going to be 93.39. But the third step is we've got to solve to actually find Y, our last silicon-30 unknown. And to do that, we're just going to take our abundance that we found, our value of X, and plug it into that equation. So 0.9339 plus 0.467, which is again our silicon-29 abundance, plus Y is going to be equal to 1. So we solve for Y, which is going to be 0.0194. So we found all of them now, so that means that we have silicon-28 having an overall percentage abundance of 93.39%, silicon-29, which was given in the question but still is 4.967%, and silicon-30 is 1.94, which is handy because all of those together add up to 100%. Just a little double check there. So it looks like we've been successful in our calculation. So I know that can seem like a lot to begin with, but the method is simple and repeatable. So I want you to have a go at a question, but if you need a little bit more time, maybe rewind, go back through this question, make notes on each of the steps before you attempt the question I'm about to put up. So this question, you're looking at strontium, which has 4 isotopes, but they do give you 2 values in the question. So make sure you take some time to read the question and use the same technique we used on the previous question for this one. Pause the video and give yourself some time. So I'm going to go through each of those steps. So our first step is to assign the strontium isotopes that we don't know, X and Y. Again, if you didn't pick the same X and Y as me, your calculations will be slightly different, but your answers should be the same. We're then going to formulate the overall expression using the calculation we've been using all lesson with these isotopes included, which is of course going to be equals to the overall atomic mass. Now, we also want our twin expression, which is just using the abundances of each of the components equals to 1. So we've got X and Y and both of our other values equals to 1. So second part is we're going to rearrange that second expression to get our Y, and once we've got our expression in the form of Y, we're going to put that whole expression into the first equation we have so that we can solve for X. And once we do this, we get X is equal to 0.0186, which of course tells us our abundance of our SR86 isotope. We then want to use this value of X in our expression for Y so that we can then find our value for Y, which in this case is going to be 0.152. Now that we have all of the abundances, we know that SR84, SR86, SR87, SR88 are 0.56% for SR84, 1.86% for SR86, 1.52% for SR87, and 82.38% for SR88. One thing that can happen when we're using this technique is a process called fragmentation. Now, at the moment, this is just an introduction to this happening as we're going to revisit it in Unit 11. But basically what happens when we look at molecules, not just individual atoms, is the high energy electrons we use for ionization actually cause the molecule to break up into pieces. This is called fragmentation. This can be in a couple of general types. So we can have the rearrangement, where parts of the molecule move position and switch position, and general fragmentation, where it breaks apart. It's important to recognize that Only the positively charged ions will be detected, of course, because they still have to follow the same path and still have to be deflected, but these will all be picked up in our final spectra, and this causes more peaks in the spectrum. And we're going to go into more detail in Unit 11 on this, but an example here is of bromoethane. You'll see the molecule here, C2H5Br. Here we have the molecular ion peak over on the right hand side, but the molecule can break. So we have the whole molecule is over there on the right hand side, but the molecule can break down into these smaller components, and these form these peaks all the way along, and we can actually use those to identify the molecule. But at the moment, I just want to introduce the concept of fragmentation as a possibility. So if you're revising this and looking back, I suggest you go and have a look at Unit 11 to further improve your understanding of this. And if you're just coming through the course, then don't worry about it too much for the moment. So what next? Well, there's plenty of questions to be looking at with this based on your understanding of atomic and molecular mass, and also finding isotopic abundance and doing those calculations in both directions. There's no practical video with this lesson, so thanks for joining me. It's nice to be starting a new unit. I hope you enjoy it, and don't forget to like, subscribe, share the videos, and as always, practice makes slightly better.